At the most fundamental level, our understanding of matter has evolved from point particles to something far more intriguing. String theory proposes that the basic building blocks of the universe are not point-like particles, but tiny, one-dimensional filaments called strings. These strings can vibrate in different ways, similar to how a musical instrument's strings create different notes. Just as a guitar string can vibrate in different patterns to create different musical notes. These strings are unimaginably small, existing at what we call the Planck length. To put this in perspective, if we magnified an atom to the size of our solar system, a string would still only be the size of a tree on Earth. These tiny vibrating strings are what give rise to all the particles we observe in nature, from electrons to quarks. Just as a guitar string can vibrate in different ways to create different musical notes, cosmic strings vibrate to create different particles. These vibration patterns can become more complex, just like higher harmonics in music. Each fundamental particle corresponds to a unique vibration pattern of these cosmic strings. Force-carrying particles like photons have their own distinct vibration patterns. Matter particles like electrons vibrate differently, and quarks, which make up protons and neutrons, have yet another unique pattern. This elegant concept suggests that all matter and forces in our universe are simply different manifestations of the same underlying stringy substance. These cosmic strings can transform from one type of particle to another through changes in their vibration patterns. This underlying unity of all particles through string vibrations represents one of the most profound insights of string theory. Our observable universe has 4 dimensions, 3 spatial dimensions and time. However, string theory requires additional dimensions beyond these 4 to work mathematically. The theory needs either 10 or 11 dimensions total, with 6 or 7 extra spatial dimensions. These extra dimensions are curled up at the quantum scale, specifically at the Planck length, about 10 to the minus 35 meters. To understand the scale, imagine if our observable dimensions were the size of a large city. The curled up dimensions would be smaller than a single atom. These compact dimensions create the complex geometric spaces needed for strings to vibrate in all the ways necessary to produce the particles and forces we observe.